Yes, well, Radek. We have just started the broadcast, right? So
Hmm?
from now, people can see us, and I hope they can hear us for sure. The the webinar is being recorded from now, so
Okay.
it's recording, and there's a new client, right? Of
Hmm.
this, and it says we have 59 minutes only, so I hope it's not gonna be terminated.
Cut off.
In,
Okay.
right? It scares me a little bit. Why there's the 59 minutes remaining only?
Yeah, because you said it for one, right? 1 hour.
And
But
do
I
you think
can
it's
you can stop the timer if you click on the
can we click it?
time window.
Stop timer. Okay. So
You can hide it. You can stop it. So I
hide
think
timer
it's
from
just
attendees so they can see it. You think they can see it?
yeah.
It
I
seems
think
they can
so.
see it. So let's hide it because no one says
We
here
don't.
it's gonna be just 1 hour. I will mention it in the beginning. So
Hmm.
I'm hiding the timer. And what else? And also we can Radek, do you think we should stop it or pause it?
I don't think so.
Like
I
pause it?
don't think so.
It's not gonna terminate us, right? It would be
I think it's just
so
informative
and
to.
it's just a timer. Okay. Okay, let's keep it. Let's risk it, right? This way.
At least I hope so.
Yeah, yeah. Yeah, okay. So, well. I think it's on my clock. It's 2 p.m. So it's actually time to start the webinar. So, what do you think, Radek?
Yes, let's go for it.
We have quite some people already here. So, yeah,
Nice.
okay. I guess it has to start. So let's start it.
Yeah.
So, yeah. And how to what to? No, I just minimize this and okay. So let's
Yeah,
start
I
the
can
webinar.
see. Yeah, I can see the presentation now. So
Okay. Well. Okay. So, hello everyone. This is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar, which is about CFD preprocessing. It's a special format. In today's webinar, we would like to dedicate our all the time just exclusively to preprocessing. Which means it's a preprocessing for us is preparing the geometry for CFD simulation. It's just preparing the geometry. So we'll be talking about how to open the geometry, how to access it, how to split it, how to clean it, and to be simulation ready for CFD. How we think it's useful, efficient, and accurate. So there will be another webinars for CFD simulation and also meshing. So today's webinar is not about meshing. Meshing will be sometimes else, but it will be about pre-processing, just preparing the geometry. There are multiple ways, so let's take a look at it. And yeah, so pre-processing. Yeah, so the webinar is being recorded, and the recording, yes, it will be later publicly available on our YouTube channel. So feel free to follow later on your leisure time, and you can break it into sessions if you particularly like something or need to review it or see it again. Okay, so the webinar is going to take perhaps more than 1 hour because we have a lot of things prepared and we have been preparing for this webinar quite a lot. So it will take yeah quite some time. I don't promise anything, and yeah, there will be couple of sessions. Let me do last check that everything works. The day with me is Radek here as usual. So hello Radek, can you see us? Can you hear us?
yes, hello Luboš, and hello all the audience. Yeah, I can see you. I can hear you. All of us
Yes.
in a good mood. I hope so.
Yeah.
Let's
Let's
go
make
for
it.
it.
Yeah. We're happy to show things as usual. So okay, so it seems everything is working. And Radek, I suggest we would switch the cameras off for now, and we will come back at the end if ever. Yeah, I mean
Okay.
on the
Yeah,
screen.
sure.
Yeah, so let's switch the cameras off for now. Yeah, so this makes, I guess, the screen ratio even better, because there will be details. I'm sure that it will be very interesting to follow. So yeah. Let's go ahead. Let's make it. So here is the agenda of today's webinar. So there will be, yeah, we have to undergo a necessary introduction. I will take care that it will take less than 5 minutes. If it will take more, I will personally buy you a beer when we meet sometime next time. So yeah, 5 minutes introduction. It's necessary. We have to say what's on the table. Then we will start with general thoughts. We want to repeat or mention the general principles, how we think, and what's necessary, what we need to do. And then we will go more a little bit to details. What are goals? What are principles? And what's the way of thinking when we create the simulation ready geometry? So Radek will show us and tell us a couple of goals and principles. What's required from a proper and professional reprocessing. And then we have a couple of cases to show. So we have, in the first case, we will show what could be an ideal geometry for CFD simulations. So we will show it. Then we have one little case in Blender, how the geometry can be operated. Then we have also an example how everything can be automated with, for example, with CF Turbo. And in the last and perhaps the biggest case, we have a complete process of cleaning and creating the geometry in Salome. It will be Kaplan turbine, and it will be I would say comprehensive process. You start with dirty something, and you end up with simulation ready geometry, and we will explain everything pretty much in detail. Yep. Then at the end of the webinar, as usual, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions anytime during the webinar. I'm sure there is a window. You can ask your questions there. And please ask your questions. It's your time, and it's definitely about you, not about us. So ask, and we will answer your questions, and we will answer all of them. So the most relevant and representative questions will be answered right away here in the webinar. Specific questions which are difficult to take anything away of it for the rest of the audience, we will answer them later via email. But all the questions will be answered, and that will be it. And I guess it sounds like a plan, and let's see what we can do with it. So yeah, I really mean it. I'll do in 5 minutes what I promise. I'll say the necessary introduction. I'm starting the timer on my clock, and let's take a look. So there will be other webinars. The next webinar will be CFD simulation setup, and there we will explain how we approach the meshing and how we approach all the boundary conditions and models and everything. So the next webinar is CFD simulation setup, and the other webinar will be CFD post processing. So there we will show how to post process and how to view the results. Again, very interesting topic. So it's basically it's series dedicated to each I would say workflow step. Okay, so those are new webinars, and here we go with the couple of introduction of ourselves. So I guess you know, but still I have to say it. We are CFD Support. It's the company name. We are located in Prague, Czech Republic. We were founded in 2009, and we deal with CFD, FEA, and FSI simulations. We do quite a lot of optimization and also acoustic simulations. We are a relatively small team, but very efficient, and we also developed software which is called TCAE, and And yeah, most of projects and everything what we do, basically we do in TCAE. We believe it's fantastic software because it's based on open source. It has several software modules, and these software modules communicate with each other and are very efficient because they were designed from scratch to be flexible, to fit any engineering workflow, to be ready for a high level of automation, to be usable in every way. It's not limited on the users' job scores or hardware installations, so the users can be sure that they can use their resources to the fullest. And there's wide range of possibilities how to use it, and yeah, workflow scenarios. It's based on open source, and it consists of more than 60 open source packages. And on top of these open source packages, we have developed more than 50 many years of consistent development in a team, which makes TCAE pretty comprehensive, usable, and ready for the usage in the industry. It's focused, it's automated, it's ready for remote computing, it's ready for computing on desktop, PC, laptop, cloud, cluster, remote computing in Windows or in Linux, in batch mode or in graphical interface. So there's really a wide range of usage. And it's been for like 15 years, it's been tested almost every day on benchmarks. There are more than 50 existing tutorials which are based on real projects we did in the past. And also we have unlimited technical support to ensure that the use of TCAE is smooth, and it brings the value which is enormous. The current release is 25.03. We released new TCAE, new versions every like 6 months. And for the future, we are definitely focusing on optimization. We believe it's the future. We also do quite a lot of acoustics, and it's it's a good spot because not everybody can do that. It's quite complex. And also we focus on the new features, especially new software modules. We are currently developing new software module called T-Base, which is something which allows the users to create to store all the results forever in special databases, to offer to play with the data and create own surrogate models, which is what we believe in. Yes, we also have the TCAE Lite version for those who have no or low budgets. And my timer shows me that time is almost up, and because I like drinking, but still I promised I will finish in 5 minutes, which is happening right now in 5 seconds. So this was the necessary introduction as promised. And let me see. Yeah, let's go ahead with general thoughts. So Radek, still alive?
Yeah, yeah.
Did you make it?
Listening and following.
Okay, that's great. That's great. That's great. So listen, I think this could be like just a few minutes of joint conversation uh, about general thoughts on CFD preprocessing. And as promised, I wanted to start with something which is more general, to start with general principles, and then go more and more into the details, right? And of course, I have some thoughts, but if I ask you now, uh, what comes to your mind or on your mind when you hear CFD preprocessing?
Yeah, I imagine that this is the first step the engineer must do before going for CFD simulation, right? Because without geometry, you have nothing to simulate. So you have to have the geometry, the input geometry, and the quality, the formats of the input geometry can cover very wide range of all the formats, quality, details in the geometry, and so on. The source of the model, if it comes from some civil engineer or it comes from a general designer, and this makes the process really complex. And to master CFD workflow, you have to also master the preprocessing, right? You need to prepare the geometry in a proper format with a proper quality, etc. And the engineer needs to know what what they expect from the CFD simulation. So what details should be included, what details should be excluded to make the workflow simpler, etc., etc. Right. So what I would say that it is the first step in the process, and it's complex, and uh, some basic rules must be followed to have a good input data for CFD
Yeah,
simulation for the
yeah,
machine.
yeah.
Yeah.
From my thank you, Radek. From my side, it's kind of yes, as you mentioned, it's a complex part of the workflow, and it's somehow it's for many users and engineers it's a bottleneck, right? Because
Mm-hmm.
it's
Mm-hmm.
there's a lot of
Agree.
complexity involved in the beginning. There are a lot of various inputs, right? And we have to make the inputs to behave nicely, right? To be like to some level they have to be generic, to be
Yeah.
usable in and automatable, right? So
Mm-hmm.
the mess is caused by the complexity of 3D space, right? Because everything is 3D and there are various formats, right? There are for example parametric models, there are step files, there are CAD files, there are like reduced geometries or the low level geometries like
Mm-hmm.
scans and STL surfaces, and it's quite a mess, right? And there is no measure of quality, right? You have to create your own scale of quality, and that's why quite a lot of experience is involved. Serious amount of skills and knowledge is necessary, I would say, and a lot of complexity is involved. What's very important to say in the beginning that is it's sometimes we say garbage in, garbage out, right? I hope it's
Mm-hmm.
clean. It's
Yeah.
clear what it means. Uh, if you provide if you do bad engineering or poor engineering in the CFD processing, it can be hardly compensated later in the process, right? If
Exactly. Yeah.
poor engineering in the beginning leads to I would say okay, pre-processing sets all the expectations, all the potential and the expectation of accuracy and quality of the results, and it cannot be uh, laterly enhanced or taken back. It's really the first step. It's the foundation of everything, and that's why it's so important, because the foundations the foundation should be solid, should be pretty good, and that may be tricky sometimes.
Yeah.
Uh,
Exactly.
yeah. So we have to. It certainly deserves a lot of attention in the beginning, and it pays off later during the process. And the rest of the process, and I'm a little bit ahead, but the CFD setup is pretty much all the time the same, right? Because
Mhm.
creating the mesh is just the process, but everybody can learn it. CFD
Yes. Yes.
simulation setup is perhaps the simplest part of the workflow, because there are certain rules, you just follow them. There are things you can do or you can't do, you're allowed to do or not allowed to do, but it's a simple process, easy to explain. And post processing is it's again a routine. Of course everything is very complex, but CFD pre-processing is bottleneck because of the complexity of the data, of the nature of the data, and also of the format of the data, right? That's why it sometimes brings issues. I would I think we can finish this session with good
Mm-hmm.
news that pretty
Yeah.
everything is automatable. Anything can be automated. Anything can be learned with experience. You can very soon or eventually get much better in everything. So everything is difficult in the beginning, but after some time it gets easier, or it can be completely automated. So the good news is everybody can get there after some effort.
Perfect.
So those are general thoughts that comes to our minds, and now I would ask Radek if you can say a little bit more, I would say level 1 details about what are the goals of preprocessing if when it's done properly, what are the basic principles, and what's the component thinking, etc., etc. So
Yeah.
I think you could uh, I'll make you presenter. Yes, there's new content.
Perfect. Okay, let me know when you can see my
I can
screen.
see your screen. I can see your screen.
Okay, perfect. So can you see the presentation, right?
Yes.
At the moment.
Yes.
Perfect. Okay, so we will continue. So we will go from more general information to more detailed information about the input requirements. So we will mention several rules which has to be followed, and you need to think about them when you start preparing the inputs and or processing your geometry. So this is the list of the main issues and the main principles which you have to follow. So first one is that for CFD simulation, of course, you need the flow path geometry. So typically, if you get the geometry from the designers, which are not CFD engineers, and the design was not uh, um, exported for CFD purposes, but for general purposes, just for manufacturing or any other goals, then the model includes all the details, and many of the details you don't need to include into the CFD geometry. So first is the extraction of the flow path geometry, so only the part of the geometry which touches the fluid and which will be defining your CFD computational domain. The second rule is it must be as simple as possible. So as simple as possible gives you the freedom of simple workflow. Simpler shape will give you better meshing, etc., etc. So typically here, CFD engineering needs to know what is important for the goals, for the CFD parameters, output parameters, and needs to decide which part should be cleaned, which part should be simplified to obtain a nice mesh and to obtain a good CFD result and accurate results with respect to the original shape of the geometry. Then to design the CFD domain in general, so including the turbomachinery designs where some part is rotating, some part is not rotating, or including porous media regions or any other kind of physics which should be included into the domain. We design the structure of creating the CFD domain by the component thinking. So it's like Lego, which has to put all the pieces together, but each piece, each component consists of another parts, which will stand for defining boundary conditions, connecting of two components or two regions, etc. So this brings me to the physical boundaries. We need to split each part into the physical boundaries, because on that boundaries, the boundary conditions are prescribed. Different boundary conditions can be defined, or with different parameters can be set, like rough walls or rotating walls, or different temperatures at the different parts of the walls, etc. From the quality point of view, we need to have the watertight property, because the fluid cannot go out where we don't need it to get out. And from the meshing purposes, the mesh domain should be closed. Otherwise, the meshing procedure can collapse, and you don't get any useful mesh. And final, for the STL generation, the triangulation refinement is also important, because this is the first discretization of your smooth smooth geometry shape. So let me quickly go step by step. So I think the flow path geometries definition is pretty obvious. So typically, if you get from your designer the CAD model of your domain with all the solids, all the parts, all the screws, even engines, and etc. So you need to extract just the inner part, the wetted part of your flow domain where the fluid goes and where the fluid works. So this is the wet surface. This I think is clear. The second part is to make the model as simple as possible. So typically, if you get a general model, in this case of the small vertical Kaplan turbine, so you need to get rid of all the screws of the parts of the all the parts which are outside of the fluid domain, get rid of all the solids, etc., to export a nice fluid domain with only parts which are creating the fluid domain. Then you can focus on the details, typically the connection of the shaft or some bearings or some gaps, which has to be included into the real model, but can bring a lot of troubles with meshing, and maybe those details does not affect the flow parameters too much. So you can exclude them. So if there are some connection bearings with some small gaps which should be problematic to solve, and some leakages or gaps are used for example, cooling the system, and you don't need to compute the cooling. You can fix them, you can simplify them too, and replace them with a simple shapes of, for example, here the shaft connection to the stator part. So all the details are important, and the CFD engineer who prepares the geometry should think about this. So this is the simplicity. Then we have the component thinkings. So in the real world, and typically the turbomachinery world, but also the external aerodynamics, like for the wind turbines or even the propellers, drones, etc. There are two main domains which we recognize as the stators and rotors. And from the CFD point of view, to connect the rotating and non-rotating parts, we need to define the domains, for which we can define the rotation, and for the other parts we can define just the static treatment. So the components basically consist of the stators and rotors, and the additional advantage that the stator parts like the ducts, etc., we can split to another component splitting for several stators, and always at the interfaces automatical evaluation of all the integral values are done. So this gives you a freedom. Then automatically, if you create it this way, you will get all the information on, for example, on the interfaces. So what does it mean, component thinking? So if you have nice cleaned geometry, so we have the wet surface with the inlet and outlets. So we need to split the domain into the rotating and stator parts. For example, we can split the domain into rotors, into the spiral part, outlet parts, outlet extensions, inlet piping, inlet extensions. So typically the CFD workflow likes extended inlets and outlets, so to make the fluid calm, or to simulate the proper inlet distribution of the velocities. So these extensions are necessary, but for example, the measurement are done just before the wheel and right behind the spiral. So we can create also the additional splitting of these duct systems, inlet outlets, etc., to make the puzzle from your turbomachinery and have defined the separate parts of your design. So which puts at the end together will create again all your flow domain, but in addition to the original CAD, it also includes the inlets, outlets, and the interfaces between the neighboring component. So this This we mean under component thinking. And for example, if I go to the TCE, so it looks like this. So this is, for example, geometry of another Kaplan turbine. So this is the inlet, this is the rotor part and the draft tube. And again, so we have these three components. On the green part, we have the rotor part, so this will be defined as the rotating part, and the other parts will be the stators. And what I will mention in the next slide is that each part of the components is meshed as a separate mesh. So this simplifies the process of the meshing, that you can focus just on the each part, on the each component. And for each component, you will define a special boundary. So from the preprocessing point of view, you need to split the surface of this component into the several parts to be able to define what is the inlet, what is the interface, what are the rotating parts, what are the stationary parts. So again, back to the workflow, this means that your input geometry, for example, if you go for this inlet part or the guide component with the guide vanes, so it basically includes the restial with the inlet, or the geometry part with the inlet, the part with the outlet from the component, blade geometries. So then you can define different mesh refinement. So this is also useful to have more more splits in your geometry, because then you can define high level of refinement on the guide vanes, for example, different level on the hub, and for example, rougher refinement on the stay. So this is the meaning of splitting the component into the additional parts, from which in the final mesh, from which the patches will be created, and on patches you can then define different boundary conditions and, for example, apply special treatment. So this is the physical boundaries. And including this splitting, we have to mention the interface alignment, because the splitting into the component requires the connection between the components, and these connections we call the interfaces. So basically, each component has the interface which can be connected to the neighboring interface, and this interface alignment matches perfectly. So you need to have a perfect match to have a good accuracy of the mapping or interpolating values from one side of the component to the other side of neighboring component. So this is the interface alignment. So you need to, additionally to the original geometry, you need to create these interfaces. This is, for example of for the radial pump, I guess. So this rotor outlet and volute inlet connection has to be perfect, has to match perfectly, because then the accuracy is the highest. There are the methods that you can connect, for example, from one side the extended inlet, or extended in the axis direction, but from the rotor, for example, you have still the narrower patch strip. But the best accuracy you will have if the mesh has nice edges and the face alignment is perfectly aligned, and then this is the highest accuracy for interpolating the values from one part to another part. So another option, for example, just an example, that you can also apply the segment geometries for rotating symmetry geometries, typical for axial fan, but can be also applied axial machines, but it can be also applied to the radial one or centrifugal one. So in this case, the interface alignment is virtual, so you can have any relative positioning of the rotor stator segment, but the virtual full wheel interface has to align perfectly. The last one is the triangulation. So if you generating the mesh with, for example, SnappyX mesh or many other meshing tools, requires the STL format, and the STL format is the first triangulation or first discretization by the triangulation of the surface. And the finest of the triangulation also define the shape for the meshing part. So what I would like to say that if your triangulation is too rough or some irregular or whatever, and include some weird shape of faces or triangles, then this also affects your CFD simulation. As an example, for example, here we have the example of rough STL triangulation on the blades, and here is the pressure distribution for the CFD results, and this is the result of the finer triangulation. So as you can see, the difference is obvious, and this can give you another torque, different torque, because your original shape of the STL doesn't follow the original smooth shape of your geometry, on which, for example, from which you then create the model and or compare with the benchmark or whatever. So this is also important for the accuracy. The same holds for the interface connections, because again on the interfaces the interpolation or mapping has to be done, and if the original shape is too zigzag or has large triangles or is too coarse, both from the point of view of STL and also then for the meshing point of view, then the accuracy also decreases rapidly with the rough refinement or rough triangulation. So this can also affect the fineness and the accuracy. And last but not least, that for the meshing of the closed domain, you need to have the closed geometry. And again, from the STL point of view, because this is the first triangulation, the best you can have and you should try to export is the watertight geometry, which means every vertex of the triangle is connected to the neighboring vertex of the neighboring triangle. The same holds, of course, with the edges. So sometimes when you export different with some approach which don't see the connection of the neighboring surfaces, for example, it may happen that some gaps will occur, typically on the connection of the curved edges, and this can gives you bad meshing parameters or bad meshing quality, or sometimes the mesh can leak out from the geometries from the geometry, and basically the meshing procedure fails. Yeah, so keep in mind that also this point-to-point correspondence is best to have. If it's not possible, then you can heal it or you can resolve it by fine triangulation, because fine triangulation gives you smaller gaps in this kind of topology of the STL triangulation. All right, so I think this was from my side of a detailed description of the crucial parts of the geometry shape and geometry requirements, and maybe a lot of them we will touch during our hands-on sessions. Respectively when I will show you the cleaning. So we will touch all these parameters and all these requirements. So I will be commenting it later during my cleaning part.
Yes,
So
yes,
maybe
absolutely. Yep.
perfect. Yeah. So
Yes.
let's go back to the Lubos and let's continue with other
Yes,
topics.
yeah, absolutely. Yeah, yeah, Radek. So let's do it. Can you now see my screen, or is it
Okay, not yet.
okay? I need to say share. Okay, I got it. Got
Mhm.
it. So I hope you can see
Yes, now
the
it's there.
presentation now.
Mhm.
Okay. So I'll continue. So this was the goals, principles, and some terms explanation. So I hope it's clear what we are looking for. We are looking for a geometry which is clean enough, simple enough, and relevant, right? That's especially important. The geometry has to be relevant to our case. So all the relevant, I would say, surfaces has to be presented. They have to be smooth enough to represent the to mimic the real geometry as closely as possible. So we have a couple of cases we wanted to show you because, of course, it differs where your data comes from, right? So sometimes it's automatically generated data, sometimes it's like low-level geometry, like STL files directly, and you need to play with them. Sometimes it's CAD, yeah, the CAD file, which needs typically needs to be cleaned and prepared for the simulation. So we have a couple of examples of each of these groups, I would say. So let me jump right into the case number one, where we wanted to show you what's the good representation of the goal, which is somehow an ideal geometry. Radek showed already quite a good one, the Kaplan turbine, which is the tutorial for TCAE. So I will just briefly go ahead with such centrifugal fan geometry. And Radek, by the way, I will be happy if you correct me if I say something wrong or no, or incomplete or something. And we have such an example, which is pretty standard geometry of centrifugal fan. And this is I would say someone did his job well in this case, because the case is split into components, and so I will just quickly show you what Radek just showed you before, but on other case. So this is the geometry is being prepared in a way what we call it the component thinking, because sometimes some geometry parts can rotate or can have different boundary conditions and can have even different physics. So it's smart to split every case into components, as it's logical when in its real physical representation. So typical centrifugal fan can have something like the inlet tube. We call it sometimes we call it suction. Then it can have the part which is rotating. So definitely it deserves its own component. Sometimes, yeah, for centrifugal fans we call them impellers. So impeller part, and then the spiral with a volute which is also necessary to make the pressure get more static, etc. Anyway, so this is an example what I wanted to show you, that a good example is to have three components which are following each other. So the flow comes into the machine through the section, and each such component has, yes, again, as Radek mentioned, it typically has its inlet, then it has typically the outlet, and then it has a wall, right? And all the components should have some corresponding order. So for example, the impeller has, again, it has some, let me see, the inlet, then it has the outlet, and then it can be split into, for example, to the shroud and the hub. And sometimes it's smart to split the blades into the trailing edge, suction side, pressure side, and the leading edge, because sometimes it's smart to have more surfaces. It's not necessary.
Yeah,
It's
that's important to say that it's not
yeah,
necessary, right? But it will improve and will give you more options to play with the mesh refinement locally, etc. But it's not compulsory, right?
Yes.
Yeah.
Yes. So we like it that way, but it's absolutely okay if you don't do that, and you will still your ambitions to good results are still high enough. So and so a good a good um, example is clean surfaces and to keep the relevant surfaces, because in fluid dynamics surfaces matter. Surfaces matter because fluid flows and all the integrals and all the important things matter, and happen all the important things happen on the surfaces, either on the walls or on the interfaces. So it's all about surfaces. And yeah, the simulation ready geometry is good set of surfaces that fit each other, I would say. Okay, and time is running quite quickly, so I'll go ahead a little bit. I have another example where we will discuss just a little bit how we can proceed when we have the STL files, because STL files we can have them from scan, or someone send them to us, and we don't have the access to, for many reasons. It may happen that we don't have access to the basic parametric geometry, but we only have the reduced geometry. But basically, those are the points and sometimes normals and triangles. So I have a little example, which is in Blender. By the way, I love Blender. I think it's really great software. It's open source. It's free to anyone. It can do a lot of geometry operations, but it's especially good on this low-level geometry. Here I mean, okay, let's call them STL files. I'll be speaking about STL files. So this is exactly the case, because we received from one of our clients this quite realistic model of Formula One, and Blender is really good on working with STL files. And for many reasons, it's usually good to have the model split into different files, because when you have different, I would say components, but yes, files, and in the external geometry especially, because it allows you to play with them, right? For example, you can replace the wheels, you can play with the wings, and uh, you can really play with them. So to having the model split into components is generally very good idea, because you can play with them, you can replace them and study their effects, right? So it's a good idea. And also the watertight property is very useful and almost necessary. It may happen that it's not possible to do that. Sometimes it happens, but usually you need to have watertight components of all the parts of your model. So let me explain or show you a little example. So I will pick something here. So I will pick this little guy. It's I don't know what it is. I think it's some kind of sensor. So let me take a look at it. Uh, so it's yeah, such a guy, which is, let me see. I'll jump into the edit mode, and it looks to me like like it's watertight. It's closed. Let me do a little check here. If you download the extension, free extension to Blender, which is called 3D Print, which is a good tool for 3D printing, we can use it also here. And if I check my component, it tells me there are no non-manifold edges. There is nothing bad. It's really perfectly closed, and it's a perfect guy. It's a perfect component. I like it. So to be able to show you something, I need to cripple it in a way. So I will pick this, and look, someone just removed one face. right? So now it's definitely not watertight, right? There's a hole in it. There's a hole in a big hole in this component, and this could be an example of a bad geometry, right? So I have look, I have formula here, and this component, this guy here, is not watertight, and this could be a potential source of problems, right? Because if I I'll click this this skeleton of the monopost, and potentially it's very highly likely if I make very fine mesh, what happens, the flow flows also inside this guy, which I don't want, of course, because it's I want to keep everything what should be closed has to be closed. Otherwise, there would be at least additional mesh cells. I don't want them there, and also these buffers and everything. So I want to keep everything closed. That's closed. It's very important. So to keep it watertight, keep it waterproof. Okay, so this brings me back to the guy. So it's not watertight, right? It has this hole, and Blender, why I'm here, I want to close the holes. Sometimes it's simple, sometimes it's easy, sometimes it's difficult, sometimes it's something in the middle. But okay, I have picked this guy, and what can I do? I can go to edit mode, so I can see the vertices, I can see the edges, I can see the faces. What's important? There are of course multiple ways. What I can do. But by the way, if I check again in the 3D print mode, if I check again, it tells me, oh, something is wrong. I have found, or 3D print function has found 16 non-manifold edges, and I can ask it to show me. So show me where the ugly non-manifold edges are, and it says, okay, Lubos, it's here. Those are let me see. Okay, these are the edges. These are the edges, and you should do something with them, right? So I can say okay. So I'm going to. It's possible to manually pick the points and then seal them with F function, right? You can play with them. Of course, this would be a little bit silly. Sometimes you want to do some engineering because the face may not be that I would say simple. So there are a couple of ways how to do. So I can use this X-ray, for example, and pick them, and then press F, which is it creates the face out of the resources I have given. Or of course, I think you got it. If I deselect everything and again ask the function to show me the non-manifold edges, I can ask it to make the manifold for me, or I can create I can seal them up with F shortcut, which is create the face out of the resource we have selected. Yeah, and if I escape it, I have it again repaired. So now this guy, now this guy is sitting on the top of the Formula One, and we can be sure that it's perfectly watertight and there will be no problems with it. And yes, sometimes when you have this low level geometry, you have to go component by component and seal them up. If you are in some research project, of course, if you're in some recurring project which is being repeated all the time, then you would need to find another solution. And there are there are solutions for everything, of course. But yeah, in research projects, you can seal everything in this way. And Blender is really good tool for that. There are many possible visualizations and also point transformations, and the games you can play. There are really a lot of them. So the point from here is Blender is good, and if you can split the model to as many closed watertight components as possible. So I will go back to my presentation. I consider this well, it's gonna be it. And let's go ahead a little bit. By the way, another just technical check. Radek, can you hear me? Is it still?
Yes, I can.
Okay,
I
okay.
can follow
Thank you.
everything, so
Thank you, thank you, thank you. Because
everything's
I
fine.
always like these kinds of confirmations that I'm not
Yes,
talking to
yes.
the wall, but someone hopefully is hearing. Okay, that's great. That's great. Let's go ahead. So I have another example because many times in especially in repeating workflows I mean in workflows where the repeatedly again and again and again and again and there are big optimization loops, you simulate the same things, you should have some kind of automation, or in other words, for CFD preprocessing you may have some parametric geometry builder which creates the geometry for you, and it's already simulation ready, right? So it's another approach, and that could be this CF Turbo. We have a very good partnership with our partner from Germany, CF Turbo, which is Turbomachinery conceptual design tool. And let me see if I can show something in it. We have just recently created a new interface with CF Turbo, so it's completely automated. So let me show you how it works. So, well, pretty anything what you export from CF Turbo, it can be automatically run in TCAE, but let's take a look. I'm picking this centrifugal pump. By the way, we love looking at rotating machinery in meridian view, but yeah, what's even more transparent is looking at the machines in the 3D 3D view. So let me check how the buttons are clicked, because it's always different in every software. Okay, right button on mouse is moving the object, left button is rotating around. I specifically like this function, it rotates for me, and the impeller is rotating now. Yeah, so now I'm in CF Turbo, and CF Turbo is very, very efficient Turbomachinery conceptual design software. So you can design all the rotating machinery machines here. It's very user-friendly and very, very efficient. And we have very fruitful collaboration with CF Turbo. And I will just quickly show you, okay, this is such a case, normal case, a normal pump. It's their standard pump. Yeah. So I'm not gonna play. I'm expert on CF Turbo. I am not. So I will just go to the export. I will find the best software of them all, which is TCAE. And for TCAE, I will export, yeah, this model. It has three components. Also, CF Turbo has this component thinking because it's very logical and very straightforward. And I can say I guess I'm going to export the geometry. It's because I did it just a while ago. It asked me if I'm going to overwrite it. I'm just going to overwrite it, and so now it's exporting, and it's being written down on the hard drive, and I guess it takes a couple of seconds. And I just did the automation. There are, of course, there are quite a lot of I would say export settings regarding the granularity of STLs, or you can export the periodic segment, etc., etc. But anyway, it's finished, and now, yeah, I did export it here, and I think I can directly open this. Hopefully, I can directly open this configuration file, and it's going to open directly in TCAE, and everything is ready for the geometry. So the point is, if you have CF Turbo, the best way whatsoever is using CF Turbo, or you can create your own geometry builder. It's not really difficult as it may look like. So we have seen really great customers geometry builders created in slightly in Python or in Salome, Shaper, or in Rhino. So, and there are many other tools which also in other tools. So there are really good ways how to create the geometry automatically. So this is the case. Yes, I can. If I click the automatic run, everything would run right away. I did it just a minute ago, and yeah, I simulated everything. And also the first thing I always look at is the efficiency, because efficiency it has everything in it, right? So if I see, okay, this pump has efficiency 87%, it already tells me that something has been done correctly, because efficiency it involves all the important quantities like torque and the pressure. So that means the simulation is likely okay. So CF Turbo is a good choice, or any other automated geometry builder is perfect for the simulation ready geometry, because it automatically does the job for you, basically. Yeah, so that's this. And yeah, time is running very quickly. It's 2 p.m. already, so 3 p.m. Sorry. So yeah. Let's go ahead. So we have the last case, the biggest case we wanted to show you. So it's the most common project scenario, which is, okay, someone has given me a cat model, which is it's a large dirty geometry, which is full of unimportant, irrelevant details. We have to somehow make it simulation ready. So the golden part of the webinar starts right now. Radek.
Okay, thank you, Luboš. I would not say it's the golden part, but it's the more work demanding part. Yeah, because the cleaning is the process of several basic steps to be done. So I suggest having a nice podcast you prefer, put your earrings and listen to nice podcast and clicking and cleaning the geometry. So you can
Yes.
do two tasks within uh, one workflow. Okay, so I hope you can see my screen. So you can.
Yes.
So
Yes. The
I
stage is
directly.
yours, Radek.
Okay,
Thank you.
thank you, Luboš. So now we will be cleaning the geometry in a really rough way that we have the geometry of the vertical turbine. So maybe I will directly load it. So now what we also like to use is Salome, which is also open source software. You can download it on salomeplatform.org pages, install it, and directly use it. So I will go to the geometry module. So Salome consists of several modules. Typically what we use is the geometry module. Then for meshing, for STL generation, and for nice STL triangulation, we use this meshing module. And there is also the geometry shaper for generating parametric models, which can be also handy, and basically you can create nice parametric models with a parametrical way of thinking. Yeah, so the shaper can be used for creating parametric models. But now we will stick in the geometry module, and here now I will import the step file we got from virtual customer, and we'll start cleaning it. And we will follow all the principles we are talking about in the first part of the webinar. So let's go for it. So here, live example, and at the beginning, I have the geometry of vertical Kaplan turbine. So I will load it, and let's go for it. So of course, you can use your favorite CAD processing software you want. So definitely some other tools could be the Rhino or FreeCAD or whatever you are familiar with, and whatever will give you features and utilities or functions which will help you to clean the geometry. So Salome is, let's say, so we can call it conservative way. So you can exploding, splitting bar, connecting part, and based on these simple steps you can clean, create, and and pre-process the geometry. So this is what we have. Yeah, so as you can see, we have all the details, so of the vertical Kaplan turbine, so you can just connect it to the piping and you can run it basically. So we need to clean it. So as you see, we would like to extract the wetted surface. We will get rid of this engine and shaft part and other compartment. So let's go for it. Maybe just to see how the impeller and stator looks like. So you can see here we have the propeller with the hub. Here we have the stator and part of the shaft. So we need to somehow explode it and clean, get rid of the unnecessary part, and maybe some parts will be modified to and simplified for better meshing. So let's go for it. So what I will be typically using is this explode option. So this explode will allows you to explode the geometry into the subshape types of several types. So typically we start for more complex shapes, because typically the CAD model also consists of each solid part. So definitely we can select those parts which are relevant for us. So here I will click on the select subshapes, and as you can see, for example, I can export just the engine, etc. So I will go for this, let's say, for the duct system, for the shroudings. So I will export these three parts first. So as you can see, so this is just the piping. Yeah, so basically the outlet part, shroud of the stator and rotor, and the inlet duct system or inlet pipe, this elbow. All right, so this is fine. Maybe what I suggest you, maybe I will not follow my typical steps just to speed up the process, but I suggest you to name each part, to simply refer to the part. So for example, what I mean, so here you can name it as stator shroud. The other part, for example, could be the outlet, and this will be the, I don't know, the inlet, or you can call it, yeah, the inlet, for example. All right, but we will also need the other parts. So let's go for another decomposition, another explode. So again, I will click on the solid. So I will hide these three parts which I have already exploded. And now what we have here, so okay, we have the hub, we have the rotor, we have the stator, and we have the shaft. Here's another item, bearings or whatever. So I will get rid of it, and I will just then simplify the shape to smooth connect to the stator, for example. Okay, so I will explode these parts, and together with my already exported parts, so I think we have everything what we need, and so we will be processing these parts. So again, just to fulfill what I have said, okay, we can name it to easily refer to these parts. So this could be named, for example, shaft. This will be the rotor, and this could be, for example, rotor hub. All right, so let's go, let's say, from inlet and to the outlet and start cleaning the system, the geometry. Okay, so let's start with this, with the inlet. So if I right click, I can click here, show only. So now what we need is to extract just the wetted surface. So on this part, I can again click on the explode feature, and here I can select now face, select subshapes, and I would like to extract just the faces from which the inner part is constructed. So I hope this one. Okay, so anytime I would like to just see what faces I have extracted, so I will hide the inlet component, and we can see, okay, perfect. This is okay, this is fine. So just to connect them together, I like to create these shells. So it will connect the faces. So I will name it like inlet and for example, wetted surface VWS. I will call it the wetted surface extraction from each part. All right, so this is the inlet, and similarly we will follow for the other parts. So another part is the shaft. So this is the shaft part, as you can see, which goes through the openings here and will be connected to the stator. So I would like to explode faces on the shaft. So let me, and what I really like that we don't see the edges here, because I don't need what is in the external part to have a nice geometry. So what I can do is I can cut the shaft by my inlet to create the contours and to be able to export just the faces. So we can do the partition, which is here. Partition function. Tool object is my inlet WS, the wet surface. I can click apply, and now I can see I have nice cutting, which is nicely connected to my inlet elbow. All right, and just to see how the stator is connected, so I will visualize the stator. So as you can see, so what I will do, I will export just these two faces, and here from this edge to this edge to close the gap, because I don't want to model the flow here, because there was some connection plate, or how it's called. So I will create nice ring-shaped face which will connect these two edges. So I will explode the shaft part in this way. So again, partition, face, and select subshapes. Click on these two faces. Now I can get rid of this, and perfect. So this I have. And now I can create a connection. So the best way to create it, for example, I can create a line connecting these two edges, and then I can run the operation generation and revolution. So I can create this straight by revolution of a line. So this I can do in the simple way. So what I can construct is, for example, to create a point. Oh, sorry. Yes, create a point on the edges. So I can create. So what I click here to create a point. Now I can create a point on the edges, on any edge. So I will first I will choose this edge. I can define the point by a coordinate. So for example, I would like to have the coordinate with the highest y axis. So y is now perpendicular to my view. So for example, I can click here to have some maximum y coordinate, and it will give me the maximum at the point on the edge with the maximum y coordinate. So apply, and the same I will do on this side. So by coordinate, apply, and now I have nice line with the same y coordinate. So it lies in the symmetry plane of these two, of the shaft and of the stator. So I can create line connection, and from this line I can create new entity, generation, revolution, and because my original the yeah the geometry was positioned with respect, or the axis of rotation follows the z axis, so I can rotate it along the z axis, and I need to create a full revolution. Click apply, and now I have nice face which connects me the shaft with the stator. So now I have these three faces, and again I can create a shell which I will call shaft minus ws, like that surface. Nice. So now I have these two parts, as you can see, and I can continue cleaning the other parts. So let's see how the stator looks like. So I will get off this inlet. I will keep just the stator and stator shroud I would like to see. Okay, so this is pretty nice aligned. And what we can see, I'm not sure if the stator blades are nicely cutted into the shroud. So this can also bring some troubles for the meshing. So if I click on these shroudings, click on the transparency. Okay, so as you can see, I don't know if it's see on your screens, but it seems that the blades are not cut into the shroud. So I will have no edges, for example, to export the nice contour of the shroud in which the surfaces of blades are cut in. So what we can do is that there is the operation, either operation that I can maybe, okay, first operation could be that I can cut off the part of this of the stator by the stator shroud. Maybe I will show you what I mean, but then this operation is more complicated. That, as you can see, yeah, there is not nice cutoff. So you can see that the stator blades are longer than the shroud radius, the inner radius, and this can bring me some troubles with the meshing, because during the meshing, the mesh snapping is done to the edges of to the boundaries of each patch, for example, and it can create me some zigzag shape that the snapping during the meshing will be snapped to this edge and not to this contour versus the stator blade contour, basically. So I can do it in this way, then I can explode it and cut off these parts. But there's a more clever operation, which is the fusion. So there is a Boolean operation and fuse, and I can fuse any two objects. So I can click on stator and stator shroud, and let me try it. Okay, Boolean driver failed, and typically, I don't know what is happening, but typically this operation remove extra edges fails to complete this operation. So if you uncheck it, and now if you see it, we have nice contour here, if you can see it. So this is exactly what we need. So we have fused these two parts. So now we can again explode the faces and get rid of the solids. So what I do, again, I will click explode. Now I will explode it to all faces, because it's not easy to pick which faces I want to keep. So I explode this fusion part, uh, uh, explode all the faces, and now we can simply manually delete the upper part. So therefore I suggest you to run some nice music or a podcast, because some operations are really boring to make and needs a lot of clicking. So it doesn't require any thinking. So just select, delete the parts, and the other parts. Okay, I don't need the inner part of the stator. And okay, I can get rid of this and also of this, because if I show you the rotor part, this right away connected to the stator. All right, so get rid of these parts, and yeah, this is perfectly what we needed, I guess. Yes. Okay, so now we have again the wetted surface, the shaft is nicely connected, the rotor will be connected. Okay, so I can again create a shell from all these faces. Perfect. So I will call it just stator wetted surface. All right. So now we have also the stator cleaned. Now we need to, let's have a look on the rotor. So rotor is nice. So we just need to get rid of this volumetric part or this solid part, inner part, which we don't need. And let me just check the outlet. So I think it's also nicely connected. So I will just then explode it, and we will be finished with the basic cleaning. So let me just visualize. Where is show only? Yeah, here. Now I will explode it again. So I will explode all the parts. Okay, and now then I will just delete the inner faces to really have only the part we needed. Okay, that's nice. So again, I can put it back to the shell, and this will be the rotor wet surface. Okay, and finally we can do the outlet. So again, let me click here, the outlet part, and this will be pretty simple. So again, explode face, and now I will, okay, this part, and now I will select the subshapes, and these are just 2 or 4, yeah, 4 faces. Apply and close. Let me see it. Yeah, nice surfaces, and I will name it outlet WS. Okay. All right. So let me check all our parts. So I will collapse these big parts. So let me go one by one. So show only the outlet. Then we will have the rotor. We have the stator. We have the shaft somewhere right here, and the inlet. All right. And when we check it, okay, there is a big hole. So I forgot also to explode the hub part. So let's go back and rotor hub. Perfect. So what can we do? So this is how the rotor hub part looks like. So okay, I will focus just on this. So I need to extract these faces, creating the surface. I don't need all the solids inside surfaces, and then I need to close this gap. I think that the shaft is connected and somehow mounted to this part. So I will create a simple face. I will just close this circle shape. So what I can do, I can create a shape for edges. So I will explode the edges on this tip of the hub. So I will explode the edges, and if you select all the edges, okay, I will just focus on this part. So edges, and here there's creating simple shapes, so I can build a face from the edges. Apply, and I have a nice face which close me this tip gap. Now I will explode the faces from the rotor hub. Okay. Apply and close. And now I will put everything together, and I will create again the shell, and I name it rotor hub WS. Okay, show only. And we have nice hub. So we have the rotor hub, we have the rotor connected to the hub, we have a stator connected to the rotor. Okay, we have this outlet part, we have the shaft. Where is it? Here is the shaft, and the inlet tube. Perfect. And just to refer to all, because this is my cleaned wet surface from the original shape. So I will create a shell from all of them. Nice. So as you can see, this is our basic cleaning. We have extracted the wet surface, and we made some simple simplification of some complicated parts. So we have created a connection here, and we have closed the gap on the tip of the hub. All right, and now what we need to do is to create. So now we did the cleaning. Yeah, I also visualized this simplification, let's say. And now what we need to create this to follow the component thinking, we need to create interfaces. We need to create the interfaces and also the inlets and outlets. So let's start, for example, with the interfaces. So for ease of work, I will create just the one rotor, one stator, the inlet section, including the stator blades. Then we will have the rotor, and the rest will be the outlet. So I need to create two interfaces. So I can create by planes. I will show you. So I will cut it by planes and create nice interfaces. So you can create a plane by point. So now we have here, for example, the best way is to put the interface just between in the gap between the stator and rotor. Yes, so typically to have to both the same sizing from the both sides if the stator and rotor are close together, because if you put too close to the edges, then the mesh refinement should be really high, which brings a lot of cells. So we need to place it in a proper way. So the best way just in the middle, and I think this contour on the hub, I think, could be just somewhere in the middle between the trailing edge of the stator and leading edge of the rotor. So I can put point on this edge, which is here. Vector is Z. So I will create a plane, small plane. Okay, so this will be my cutting plane, and using this plane I will create the interfaces. And the same I will do on the other side. So here, what we can do, I will create a point using which I will define, what I did, using which, okay, I just modify the camera view. So let's go back. So now, for example, here I have the edge behind the stator, behind the rotor trailing edge. So I will create a point here, and because I have no, I'm somehow I have a space where to put the interface, so I can create a larger space behind the rotor, so I can move the point more further. So for example, 1 centimeter behind this contour. So I just click here, and then I just modify the Z coordinate. And then I will use this point to create a plane. So vector in the Z direction, I will make just smaller size of the plane. And now we have these two planes. So first, what I will do, so I would like to create the interfaces just in my flow path. So I will check these two planes, and I will cut them by my cleaned surface. Okay, so now I have these two faces, so I can explode them and extract just the faces, which creates me the interface. So I will extract this one and this one. Okay, so I have these two interfaces now. Yeah, here's my wet clean surface. So I have now these two interfaces, and what I would like to have also is to have the contour right here in my shroud section, because then I can just export this part as a shroud for the rotor, and the rest for the outlet piping, and the rest for the stator shroud, for example. So what I need to do is to cut also my cleaned shell, this clean part, by my planes. So I will do in the opposite. So this is my object, and tool objects will be these planes. Okay, apply, and as you can see now, I have these two contours which will define me the boundaries for exporting these parts separately for the rotor. All right, so this is it. Now I need to put everything together. So maybe first I will also create I need to close the inlet and the outlet. So I can do additional splitting or exploding. So I will create partition, edge, select subshape. Now I will choose these edges at the end. Okay, these two edges. I will click here, create a face, perfect. And the same I will do on the other side. So explode, edge, select subshape. Okay, and I will do it manually. So here I have 3 edges, I hope, and now from these 3 edges I can create a face. Perfect. And now I can what I have. So where is my okay, so here is my partition, just to see what is inside. So this is my partition. Now I need to also include the faces, the interfaces, and my inlet and my outlet. And this I will put into my whole object. So let me check if the shell will work. Okay, if not, because of some not perfect connection, I don't know why, so it will just create a compound of shell. So I have the object, I have a simple object under which I have all my wetted surfaces and interfaces and inlets and outlets. So this is basically, I'm done with the cleaning. I just need to make a transparency just to see that the interfaces are included. Now I have the inlet and I have also the outlets. So this will be this is the part of the cleaning. So let me save my project. I will go, okay, I was there, sorry. So my today's example, cleaning, I will call it the part with the extraction of wet surfaces. Okay, so this is what I needed. So first I have prepared the geometry, I extract only the necessary parts, I created the interfaces, and I closed the domain with to have the inlets and the outlets. And now I need to create the STLs, and also I need to extract the parts which I need for the boundaries or for meshing purposes. So basically now what I need to do is to create these kind of splittings, and because the splittings is already done, I need to just assign or name the parts of my geometry of my surface. So I can name it as all, like I have all there. And now what we need to do, and it's, let's say, other boring stuff, is to create groups on my surface. So I need to create groups based on the faces. And now you need to name each part separately to be able to extract it separately. So basically what you need to do now is to select parts and create a name. So I will name it, for example, this is stator inlet, and this face creates the stator inlet. Now I can create apply, and then what you will see is that here in the pipeline browser, now we have the group here, and then we can refer or export it or create a triangulation, whatever. So this is another task is to create the groups. So for example, you need to do it in this way. So what I like, I select some parts of the new group. I will click add, and then I will hide what I have chosen just to see which parts I need to add. So hide. Okay, so perfect. So this will be the elbow, and I will name it as stator wall. So this will be my stator wall. In the same way, we can continue. So, for example, now I will create a stator shroud, height, and also the strips, I think, belongs also to the stator shroud. Yes, so I will also add these face strips, add just the height. Okay, and this will be my stator shroud. Yeah, and in the same way, you need to do the rest. So, for example, what I also like, if you here select all your groups which were already defined, you click here add, then to click into this list, then you hit Control A, like select all, then you can click hide, select it, and remove them. So now you can continue with splitting. So for example, now you can create a shaft, you can create a face pressure side, stator pressure side, etc., etc. So now I will jump in time. So I will save my project, and I will open the project where I already named all these groups. So I think here workflow, and one of my project is here groups. So I keep my fingers just to have everything what I need. Yes, so perfectly. So this is my shape. This is my shape. And okay, and what I haven't shown you yet, that is that you can also create some additional extension. So for example, a new component which extends the inlet, and this will be also created as a new component just for the extension, which I haven't done in the live example. So, but you can create pretty simply. Maybe I will quickly show how it can be done. So if you have the face, I have it maybe here somewhere. Okay, or I can show for the outlet. Yeah, so you can click on the face which we have created. You can create operation or sorry, new entity, generation, extrusion. Now you set the direction of the extrusion, which is Z, and reverse, of course. And here you just select the distance of the extrusion, and in this way you can create quickly extrusion. Then you will create a shell or compound of shells to have a single object, and then you will create the groups on them. Yeah, so in this way you can create nicely extrusion if required. All right, so now what we have is the groups definition. So what I have here, for example, I have created the stator shaft, yeah, stator hub, and splitting of stator blade leading edge, trailing edge, pressure side, suction side, stator shroud somewhere, inlet shroud. So maybe, yeah, it's bad naming, but this is the stator shroud, etc. So now one option is to extract the STLs directly from these parts, but what what you can face that, because each part will be extracted separately, then the point-to-point correspondence will be corrupted. So let me show you the example. So okay, you can click the part, you can directly click here, file, export STL. Okay, and I will export it here. So okay, I will export it here. So stator hub, I will click save, And the same I will do, for example, for this interface, just to have the common edge, just to show you the if everything will be fine or not. So this part, okay, I need to go for file, export STL, save, and now I will go on my disk workflow, and here I have these two parts, so I will open them in ParaView just to visualize what type of discretization was directly exported. So this is the interface. So I will, where is it? Here I can choose surface with edges, and to this, okay, here I will choose 3D view to be able to adjust the view, and now I will add the stator hub. Again, surface with edges, and this is basically, yeah, what you can see. I think if we zoom, this is the, okay, I render view. I hope you can see the gap here, because it's not point-to-point correspondence. So basically, this is connected to the problematic I have shown you on this slide. Yeah. So this will not this will not force this exporting the parts separately will not ensure you the point-to-point correspondence of the connecting STLs. Of course, you can, if you're exporting it, you can increase the deflection, yes, which makes the STL export finer and the triangulation finer. So let's check it. So this was the interface. So I will hide him and I will open the new one. So now surface with edges. So I know it will be visible. So this was the original one, and this is the more refined. But still, the problem is much more. So also you need to refine more the stator, and all the parts should be refined to the same level and to the pretty fine level. So, but the second choice is to create or generate the surface triangulation using some advanced algorithm, which you can do here in this mesh component or this mesh module, and it is done pretty easily. So you will check on which shape you would like to create the surface triangulation. Here you will click on create mesh. We need to have the 2D mesh because we do not have solids, we have just the surfaces, and the best algorithm is this NetGen 1D 2D, and here you will define the triangulation. So what I can set some basic one. I don't know, let's try this one. So this means that the largest triangle will have 1 centimeter, and the smallest triangle will have a 5 millimeters. So I think it will be too coarse for the edges. So let's try 0.5 millimeter. So okay, apply and close, and now by this compute, or you can right click the predefined mesh, and here you can somewhere run compute. So now the triangulation is running. So it basically discretize the surface based on your input geometries and following the triangulation parameters. So I hope I don't put so too many refined mesh. So maybe let me cancel it just to speed up the process, and maybe I will set it to more rough mesh. So again, I can click here just to modify. Okay, and I will put, for example, this one. So of course, this parameter also needs to follow all the details in your geometry. So if the edges of the rotor blades are, for example, of 1 millimeter size, so then you need to go lower for for the minimum refinement level to be able to properly discretize these curved areas and curved shapes, basically the shapes with a high curvature. All right, so this is it. So now, as you can see, we have a nice, pretty nice triangulation with point-to-point correspondence. Here, if you have the mesh and group on the faces, so you can, for example, we can visualize this stator hub. Okay, and I will get rid of the whole mesh. So this is our stator hub, and if I visualize also the interface between the stator and rotor, so now we can see perfect triangulation and perfect matching. So the same holds, for example, for the edges. So if you visualize the edges, so for example, you have pretty coarse edge refinement, so this should be smooth. So what you can also do is to create some submesh refinement. So you have a general refinement parameters, and then you can apply additional refinement parameters for the algorithm on the separate parts. So you can create a submesh. I can create them on the stator, for example, stator blade leading edge. And here I will put new refinement. And for example, here I will put half a centimeter. Oh, sorry, half a millimeter. Okay, apply, and just quickly, okay, maybe what is also good is to name the submesh with the same name like the geometry input. And now I can click compute submesh. Let's see what will happen. Okay, and now you can see that, yeah, it's much refined and much smoother. And the same way you can apply on any part of the geometry. So this brings me to the last. So I will open the surface meshing. Okay. So in this example, I set all the meshing parameters everywhere to have a nice and smooth meshings. So for example, when I show you the stator hub and the edges, so you can see we have nice smooth triangulation, and now we can simply export each part separately, which is another boring stuff here in Salome. Unfortunately, there is no one button export for all the parts. So basically, what you need to do is to put export on any part, and basically export each part separately in this way. And if you do it, at the end you will have the list of all the STLs which are ready to be used for setting the T-mesh and applying for CFD application in TCAE or in any other tool. Okay, so let me show you how it looks. So we have now all the STLs needed for both defining the components and defining the boundaries. So if I group them just to have a different coloring, just to see how the mesh is split. And okay, for example, this coloring will be better, for example. And what I can do, I will create okay, for example, clip just to see inside. So this is our splitting. So here we have the inlet duct component, so inlet with inlet piping extension. Then we have the stator part where the boundaries are the interfaces and of course the wet surface. We have the rotor part, and we have the outlet part. And because the shaft is a separate part, we can set it as rotating. The stator we can set as not rotating, and the same for the rotor part. Everything will be rotating except the shroud. And because, for example, we have separated this blade cap part separately, so then we can put high level of refinement to really to nicely match this gap between the shroud and the blade cap. So in this way, this is basically what you need to do for cleaning your geometry. So as you can see, the input geometry was not so easy and so clean, and we were be able, okay, some steps I speed it up, but anyway, within 1-2 hours, you are able to process your shape, export the STLs, and have everything ready for the CFD workflow. All right, so I think from my part and the Salome application and the cleaning point of view, I have shown you what I wanted. So I think we can go back to Lubos to conclude, and maybe Lubos will have additional note to my workflow. So
yes, thank you, Radek. Thank you very much. It was perfect. I liked it very much. I enjoyed it. I followed closely. And
perfect.
yes. I think we can keep you as a presenter, and
Okay.
let's, because soon we will move to Q&A. So I would ask now the audience to ask your questions. We will do our best to answer them. All of them will be answered. So take this opportunity to ask the questions. We'll do our best to answer. Uh, Before we go to Q&A, I have a couple of questions. Sorry, a couple of notes to this. Yeah, this is what Radek have shown. Is, I would say, it's Champions League, right? It's the perhaps the best what you can do, what you can do with it. So it may have looked a little bit complicated, right, and complex. Where in fact it's not. You will very quickly improve when you do this, and not every time you have to do this, right? This is like more like a project work with the, I would say, with the highest ambitions to fit the measurements, really do the benchmarks. So this is, yeah, this was the Champions League. So everything can be either done simpler, faster, to neglect some details, so to make it easier to some level. And so this may have looked difficult, but it's not the difficult. Everyone can learn it. I sometimes make a parallel to riding a bike or driving a car, right? No one is the best
Yeah, right.
driver the first day. No one is the best bike rider the very first day. But after some time, it gets so much easier after some practice and learning some skills and knowledge. Yeah. So this was the cleaning of the step file of the dirty geometry, which is simulation ready, and I would say such geometry has the highest options to meet the best possible results. And by the way, for hydro turbines, we can get nearly perfect results with this uh, geometry. Okay, so it was this. There are another scenarios, right? You can have some geometry builder which is preset. Almost everything can be automated. Almost everything can be made easier. But this is what could be your highest ambition to do this. Okay, so let's move to the Q&A. So let's keep Radek presenter still, and I'm going to open the questions if I see one. Let's answer them. So Stefan is asking whether the recording will be available. It's a typical question. Yes. The recording will be available, and you will be notified via email that the recording exists. So you can see it, and you can I think at least the Radek's last case can be created from scratch. Also, the cases are available. It's not proprietary geometry. It's open, so we can give you the cases and also the project and everything. And also we will continue with this geometry in next webinars, where we will create the mesh for it. We will create the simulation setup, and we will do the post-processing of this geometry and similar geometries. So all the geometries we show in our webinars are freely available. So just send us an email. We will share it with you. Okay, Vanessa. Hi, Vanessa is asking, can I set default settings for the meshing and load point and so on in CF Turbo. So I don't have to change it every time. Yes, you can do that. Well, yeah, for the simulation, you have most of the settings right away in CF Turbo. You do it there. You say what's the flow rate, what's what, and this single point is loaded directly in TCAE. And yes, this single point can be simulated right away, absolutely automatically. You do not need to set anything. Maybe number of processors, because typically the default number of processors is, I think, 6, but that's detail. The rest is perfect. And yes, the when automated, and you can set the other simulation points. You can add more like higher flow rates, lower flow rates to receive complete characteristics. So it's pretty much ready for that.
Yeah,
Yes,
yeah,
automated with CF Turbo.
yeah. And if I can add that,
Absolutely.
you can
Yeah.
also, if you have a template, for example, from the point of view of the TCE, and you have your best setup, so then you can just replace the input geometry, and the rest remains the same. Yeah, so you can have your template set up for the TCE, where you have the best results, for example, and then you can just regenerate and re-export new shape of your geometry and run the whole workflow with the new set of geometry, and you don't need to reset or modify any TCE parameter again.
Yes.
So
Everything
yeah,
can
I
be
think
highly automated. You can just uh, you can just modify XML files and just rerun CF Turbo and together with TCAE anytime. Just change the parameters and receive new results, and you can run it in the loop. And there are endless options how to do that. So yeah, it's highly yeah
yeah,
synergy
yeah.
in these
And
terms.
there is also a simple connection to the T-opt, right? So the T-opt can manage these loops. So this is
Yes.
also the part of the automatization.
Yes, I'm looking where the questions are. Yeah, also another question from Vanessa, which is the original one. Is the component map created automatically? Yes, the component map is which is part of any TCAE setup. And yes, when the geometry is created in CF Turbo, then the geometry the geometry is well, yeah, sorry, it's
Mhm.
in Tmesh.
Yeah,
Then the geometry is inherited from CF
yeah,
Turbo, and also the component map is inherited. So there's typically some suction part, some rotating part, and some spiral or volume
yeah.
part.
Maybe
Yet yes,
you can
yep.
also show it on the CF Turbo example if you have still open it, but I'm not sure. Yeah, here
I
we
could
get.
show, but I would only embarrass myself because I can't
Okay,
work
okay,
in CF Turbo. But
okay, okay,
yes,
okay.
I guess you can.
No,
Uh,
I mean in TCE, but exactly for this export. Yeah, for this.
Sure, it's here.
This is
It's
what I
here.
meant. Yeah.
It's this one. It's this one. It's
Yes,
this
yes. So if you go
centrifugal
to the
pump.
T-mesh, then there will be the component map automatically created. Yeah.
Yes, Radek. Thank you. Sure.
Yes.
Yeah,
Because
absolutely.
yeah,
I'm.
when you export it and load it into TCA, it is ready for the computation, right? So this is some default parameters are set and it is ready to run. So it will give you first impression of the results, and then you can of course play with the setup to achieve more accurate or
Yeah.
with different flow
Yeah.
rates,
Yeah. Yeah.
etc.
Yeah. But the principle is the same. It's the if you have the options, and if you can create the workflow yourself, just put it in the components. And in the component graph, you can see the flow, how it goes through the first component to the second one, to the third one, to the last one, and via which interfaces, and you can see it in the map. And of course, the map can be so much more complex than it looks like,
Mhm.
right? If you, for
Yeah, yeah, yeah.
example, maybe a quick example. Yes, I have it here, right here. Uh, there could be workflows with much more complex topology, and even so much more complex topology. This is just a simple external something, and the topology can be with more interfaces. Uh, But the point is there's a lot of flexibility involved. Okay, so let's go ahead with the questions because we are pretty long here. Yeah. Questions. So Radek, if you see some question, please go for it, and I will do the same.
All right.
Okay,
Okay,
Konstantin.
there is a question
Cancel.
from
Yeah.
Matthias. Hello, Matthias. Does the skewness of triangles in STL affect the mesh quality, skewness or edge refinement in SnappyX mesh? Well, it uses the triangles just to define the surface boundaries. So if the skewness itself affects the shape of the edges and the shape of the surface itself, then it can affect the mesh quality. But in general, it should only if it's followed with some additional flaw or the error. So in the first way, in the first point, the snapping is done to the edges. So if the generated edges are okay, then it's okay. And if the shape of the surface is still good, even for the skewness of triangles, then I think the impact of the mesh quality is pretty low.
Yeah, I think so. Radek. I think the skewness and the bad shape of triangles, unless they're completely distorted,
Yeah.
right?
Yes, yes. Because it just defines the shape. It doesn't
yeah,
use any property of the triangles
yeah.
itself. Yeah.
Yeah. But in general, we recommend, but Radek said it, I guess. The basic triangles should be finer than the mesh, right? Otherwise it would not make a sense. So the basic input geometry triangles should be finer than the resulting mesh or expected mesh or requested mesh, if you know what I mean.
Yeah. Yes. Another question I see
Yep.
from
Yep.
Zachary.
Okay.
Do you have any preference between Blender and Salome to pre-process the geometries? So, for example, I'm more expert in Salome and Lubos is more expert in Blender.
Good
And
one.
for example, in Salome, you can't process the STLs. So Salome can handle the step files, IGES files, etc., etc. But fine STLs cannot handle because it treats every triangle as a new face, and it's almost impossible to directly import STLs and play with the STLs. So to process the STLs and heal them or modify them, it's definitely better Blender. And
Yes, and
for example, from my experience, but
yes.
I almost 99% of preparation I do in Salome. So,
Yes,
but
yes, yes.
Blender has many features, but
I
also
would,
for
I would,
rendering,
I would
right, and
only,
visualization, etc. So,
yeah. I would only mention that if you have like high level geometry step files, then Salome is definitely better. If you have low level geometry, like some scans or some 3D data like STLs and nothing else, just only STLs, then yeah, Blender could be better because it's so much more ready to operate these low level geometries. So it depends. There are also other tools, right? Like FreeCAD. We don't use that much FreeCAD, but we have heard it's not that bad. There's also Open Cascade, right? Which is also possible to use. And we know that, for example, Rhinoceros is it's not open source, but it's really I would say affordable, and it's definitely really great software which can be highly automated. Geometries can be parameterized with Grasshopper, and also it's very usable for these simulation loops, parametric loops, and parametric optimization workflows with TCAE. So there are a lot of options, and pretty much it depends what's your basic source data, what are your ideas, what are your strategy, and if you don't know, we'll definitely be ready to help you or give you advice. Okay, questions.
okay, I have another interesting
Yeah,
one, so
please,
maybe I can
please.
mention it. It's a question by Wolfgang, and the question is: when meshing interface surfaces with the same level of refinement in Snappy, will the mesh be identical on both sides? The answer is no, yeah, because the meshing are done separately, so it's not connected to the neighboring components. So it's like two separate meshes then connected together. And in general, if the background mesh topology and sizing is the same for meshing both sides, then the mesh will be, and with the same level of refinement and the same level of refinement of the connected surfaces and the parts in the neighborhood of the interface, then likely it will be really similar, but not the same like applying for cyclic boundary condition or whatever. But in general, they are not identical because
mhm.
it is meshed separately. So this is a good question, but it's connected by the AMI, and if the interface curvature is, for example, flat, like for these interfaces, then the mapping is very accurate. If you have these interfaces on for example this circle or cylindrical shape, like for centrifugal uh, pumps or fans or whatever, so then a higher level of refinement will give you more accurate interpolation, of course.
Okay. Yeah.
It's a good question. Yeah.
Him is asking how compatible are SolidWorks for surface models to be used in CFD? Uh, uh, to be honest, we do not know much of SolidWorks, but we know our clients use it, and I would say it would be very similar. The principles will be very similar to Salome, and it must be achievable. The same workflow has to be achievable in SolidWorks as it is in Salome. I do not know about the surface meshing features in SolidWorks, but I guess that there must be something for it. So very similar. The principles are universal, and the tools to be used are yeah optional, always optional. And yeah,
Yeah.
yeah,
There was some
yeah,
question
please.
connecting to the refinement of the interfaces. So this was just the generating the interface from the STL point of view. Yeah, so it does not affect the 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 mesh which is generated on the interface. It just defines the shape of the interface for the meshing. So the mesh is not it was not done in here. It We just generated the STLs.
Yeah. Yeah. The mesh will be the object of some other
Yes, or the
webinar. Or
perfect.
actually
Just to be
the
clear,
next
yeah.
webinar will be about it. Okay, let's go ahead. The Makie is asking what software should I use to simulate liquid rocket motor, turbopump, and combustion chamber. Uh, uh, yeah, again, it's not ripped in stone what should be used. It depends what are your basic data, where you start from, right? If it's some cat data, you should use something like cat. If you have some low level data, then it's always question. This is difficult to answer, but if you also there's also a question if you have some budget for it, or if you strictly want to need to go for open source. Salome is always here, Blender is always here. Depends. Yeah, the same answer we have shown, just the principles that are universal, and it's up to you how to use it, and uh, depends on the details of every project. Okay. Okay, I think Radek, it's time to conclude.
Yeah, we are more than
There are
2 hour
several.
long. Yeah, so
Yeah, yeah,
we
yeah.
will answer all the other questions later, right?
There are other questions, but we have just made this Q&A. Thank you everyone for it. If you have other questions when you see the recording or whatever, just feel free to contact us. It's universal advice and suggestion. Just contact us anytime, and we will come back, and we always talk to everyone. Yeah, so this would be it. This would be it, and I would like to thank you all for your attention, who made it your our heroes, because we were like more than 2 hours long.
Yeah,
So
yeah.
thank you everyone for your attention. Feel free to come back anytime, just for a question or just say hello, and let's see what we can do together. And we will leave you with that. And bye bye for now.
Thank you and bye bye. Have a nice day.
Bye bye. Thank you. Bye bye. Yes.